Hi, in this video, we will develop a systematic approach to analyzing heat engine cycles using PV diagrams. We are going to use a simple cycle so that we can illustrate the approach rather than trying to calculate for a realistic heat engine cycle. So let me draw the pressure volume diagram for this toy model cycle. So this would be the point for the low pressure, low volume, high pressure and low volume, high pressure and high volume, and high volume, low pressure. Let me give labels for these different pressure and volume points. Alright, so this is a pretty simple cycle that makes calculations easy. All these processes are isochoric, isobaric, isobaric processes that makes calculation of work done fairly simple, and we'll be able to do this question using only algebra, no calculus needed. And having drawn this diagram, I can tell you that this completely specifies our system. This is through the ideal gas law. Pressure times volume is equal to nKT. Okay, maybe not completely specified. The number of gas molecules is still left as unknown. So if the question were to give you how many number of molecules there are, then it is completely specified. For every point along the cycle, you can actually calculate the temperature. All right, so here are the questions that we would ask in analyzing any heat engine cycle. They are, what is the net work done? It's kind of important. It points at the entire purpose of a heat engine. And for Reasons-Will oscillator, it's important to know how much heat was transferred into the system. We'll call it QH for heat transfer at high temperature. And also for Reasons-Will oscillator, the heat output from the system is also important, which we'll label QL, heat exchange at low temperature. Now here, work done calculation is actually easy. Let's say we are starting at point A. Then the system undergoes isochoric heating, reaching point B. No work is done throughout this process because the volume doesn't change. And then the system undergoes isobaric expansion, reaching point C. It does some work. That would be the area under the curve here. Then, as the system undergoes isochoric cooling, reaching point D, no work is done again, no change in volume. And then, as the system goes back to point A, undergoing isobaric contraction, the system does negative work, or rather the environment does work on the system. So the negative work with magnitude equal to the area under the curve is done. So when you calculate the net work done over a cycle, it's the area enclosed by the loop, or this area in green here. Alright, so it seems like network calculation won't be that difficult. Some of you probably have an answer right now already. So what the point of the next 15 minutes or so is going to be is actually calculating the net heat flow. So on this PV diagram, the information about heat isn't readily apparent here. So it must be calculated. This is where we are going to use the first law of thermodynamics. Change in internal energy is equal to net heat flow minus the work done by the system. All right, let's dig in. Let's just start from point A to B. So we can start by figuring out the amount of work done. That was easy. Now, as I said earlier, knowing pressure and volume specify the temperature. So we can calculate the change in internal energy. Oh, but we are going to specify a little bit more. So I guess for this system, I'll have to say it's a monatomic gas. And I hope you remember from earlier chapter that for monatomic gas, internal energy is given by 3/2 nKT. So they don't actually need to specify the number of molecules. I can re-express this in terms of pressure and volume. This is just the 3/2 pressure times volume, right? So for the process A to B, change in internal energy is 3/2 PHVL final point minus the initial point PLVL. Alright, since the work done was 0, this is equal to heat transfer along the process A to B. Now, if you look at this expression, you can see that that's going to be a positive number. So there's a heat input into the system as the system goes from A to B. All right, let's keep talking through. So process B to C. Here the work done isn't 0. It's pressure times change in volume. You can see that it's doing positive work. And the change in internal energy is 3/2 times difference in pressure times volume. I'm going to keep them as separate terms because that's going to make our later algebra a little bit easier. Now this time this isn't the heat transferred. We have to use the first law. That is, heat transferred is change in internal energy plus the work done by the system. Alright, that looks a little bit complicated. Let me do the algebra on a separate piece of paper and then just write down the result here. Alright, there it is. So if you look at that expression carefully, you can say it's a positive. So there's a heat input going from B to C here also. Now, I can sense that for the next two processes, CD and DA, there will be heat outflow. So this seems like a good location to pause for a bit and calculate the heat input, QH here. So QH is QAB plus QBC. Let me again write that down on a separate piece of paper and copy the result here. I have canceled out some terms, and this is the result. Let me highlight it so that I can find it on this very complicated page easily. Alright, let's keep going. Process C to D. Again, work done is 0. It's an isochoric process, no change in volume. For the change of internal energy, it's the same deal. 3/2 times the difference in pressure times volume. And since work done is 0, this is going to be equal to the heat exchange from C to D. Now, I don't want you to miss it. I want you to see that when you stare at this expression, this is going to be negative. So heat flows out of the system in the process C to D. Alright, let's keep going. D to A, back to the starting point. So here there's a non-zero work done, pressure times the difference in volume, and because the ending volume is smaller than the starting volume, the work done is negative, meaning the environment does work on the system. Change in the internal energy is the same as before, 3/2 times change in pressure times volume. And as before, because there's work done, the net heat transfer is not just the change in internal energy, but the change in internal energy plus work done. Or, writing it aloud, 5/2 PL minus, again 5/2 PLVH. So that's the result. And when you look at this expression carefully, you can see that it's a negative quantity. That means as the gas undergoes process D to A, there's a heat outflow. Alright, that completes the cycle, and we should calculate QL, the net heat outflow from the system over a cycle. Now, by convention, both the QH and QL are defined to be positive quantities. All the formulas you see in your textbook will assume that. So here, instead of adding QCD and QDA, I will calculate the minus of QCD plus QDA. This will give us the positive quantity we are looking for. Alright, this is going to take a little bit of algebra, so I'll do it on a separate piece of paper and write it down here. Writing down the positive quantities first. All right, let me highlight this quantity so that I can find this expression easily in a little bit when I'm looking for it. All right, that's it. That was a little bit of tedious calculation, but we are almost done. We need to calculate the network, which would be work done along BC plus the work done along DA. This is negative. So let me do that and write it down, factoring it as needed. All right, we are done. This is probably what many of you guessed a while back when we talked about the area enclosed by the curve being the network done. So with these results, there are a couple interesting things you can do. I guess I will leave you to do one of them and I will work out the other thing in this video. So one of them you can do is, this is what we would claim based on conservation of energy, that net work done must be equal to heat transfer into the system minus the heat transfer out of the system over one cycle. You can show that from the algebraic expressions we have derived. I'll leave that for you. What I want to do is a bit more interesting. I want to help you start developing some number sense for these thermodynamic problems, which is also going to be important when we start talking about efficiency and second law of thermodynamics. So let me just assign some reasonable numbers for this pressure and volume. So let's say that the high pressure is about 2 atmosphere, or approximately 200 kilopascals, or 2 times 10 to the 5 pascals. And let's say that the low pressure is half that, about 1 atmosphere, or 10 to the 5 pascals. Let's have some reasonable volume numbers too. Let's say that the high volume is 2 liters, or 2,000 of a cubic meter. Everyone here can imagine what 2 liters looks like, right? Imagine a large soda bottle. And the low volume is, let's say, half that. Alright, so what we are going to do is we are going to calculate some numbers based on these given parameters. Now watch how I don't have to specify the number of gas molecules. If I have few molecules, it means the thing is at high temperature. If I have large number of molecules, it means the thing is at low temperature. Alright, let me make some space here, taking care not to erase the expressions I need. Alright, I think I avoided erasing anything important. So as a reminder, this is QH and this is QL. Alright, so the work done is pretty easy to calculate, so let's do that. That's the difference in the pressures, that's 10 to 5 Pascal, times the difference in the volume, that's 10 to minus 3 cubic meter. And since these are basic SI units, I'm just going to trust that the units work out to unit of joule, which is what it's supposed to be. So 10 to 2, that would be 100 joules. Alright, fairly reasonable number. Oh, let me move these two things so that there's some space to write down the numbers. Alright, and let's plug in the numbers for QH and QL. The heat input is, let me pre-simplify some numbers. And all of this is going to be in joules. So power of 10 is 10 to the 2, so we're going to multiply by 100 later. 4 times 5 over 2, so 10 minus 2 minus 1.5 is 6.5 times 100 joules, or 650 joules. Huh. Does this number seem large to you compared to the work done? Yeah, it's pretty large, and that's what I mean by number sense. So actually, without doing any further calculation, because you can read this here, the net work done is QH minus QL, you can kind of figure out what QL is. And if you doubt me, you can plug in the numbers and do it for yourself. So here QL is going to be 550 joules. I just want you to look at these numbers here. In this heat engine, when 650 joule of heat energy comes in, of that, only 100 joule is turned into mechanical work. And a vast majority of the input energy is expelled as what we are later going to call waste heat. So I think that's everything we can do with this toy model here. I'll have one more toy model for you to look at where the calculation is still relatively simple and we can again plug in the numbers and get some intuitive feel for it. Until that next video, then bye.